Oxidation reduction reactions, also known as redox reactions. When we talk about redox reactions, the first thing we have to do is deal with what are called oxidation states. And oxidation states are a way to keep track of electrons during redox reactions. Oxidation states of covalent compounds are arbitrarily assigned to certain atoms. It doesn't mean that we're looking at actual charged ions, it's just a way to keep track of electrons. So let's look at some rules for oxidation states or oxidation numbers. If we look at a free element, the oxidation state for that free element is always 0. And what we mean when we say a free element, we mean an atom that's not bonded with other atoms in a compound. So some examples: sodium, or oxygen, which is a diatomic molecule, or iron, or mercury, are all free elements, where they're not in combination with other types of atoms to form compounds. So they all have oxidation states or oxidation numbers of 0. Monatomic ions. Remember that the prefix mono means one, so we're looking at ions that are made of only one type of atom. And the oxidation state on monatomic ions is the same as the charge on that ion. So when we look on the periodic table, the charge on sodium in an ionic compound would be +1, so the oxidation state would be assigned as +1. Chloride is in group 7, so it has a monatomic ion charge of -1, so its oxidation state would be -1. Calcium is in group 2, or the alkaline earth metal group, which has a charge of +2, so its oxidation state would be +2. Fluorine. When fluorine is in compounds, it always has an oxidation state of -1. Oxygen. When oxygen is in covalent compounds, as well as when it's in ionic compounds, its oxidation state will be -2. So if we were to look at carbon monoxide or carbon dioxide or sulfur dioxide or sulfur trioxide, oxygen would be assigned an oxidation state of -2 in each of those compounds. Hydrogen. In covalent compounds, when hydrogen is in combination with nonmetals, hydrogen will always be assigned an oxidation state of +1. Our last rule is going to help us to figure out the oxidation state on any other type of atom, because the sum of the oxidation states must be 0 for a neutral compound, and the sum of the oxidation states on a polyatomic ion must add up to the charge on that polyatomic ion. So here are some examples. Let's say we want to assign the oxidation states or the oxidation numbers for all of the atoms in carbon dioxide. Well, when we look through our rules, there is no specific rule for carbon, but there is a specific rule for oxygen. It tells us that oxygen is assigned an oxidation state of -2. Well, we've got 2 oxygens in this particular compound, so -2 times 2 gives us a -4 charge. This has to be neutral overall, so that must mean that the oxidation state assigned to carbon must be a +4, because that will give us a +4 for carbon, a -4 for oxygen, and a sum of 0 for that neutral compound. Let's look at sulfur hexafluoride. Well, we know that in compounds, fluoride is always assigned an oxidation state of -1, and the sum has to be 0. So -1 times 6 gives us a -6. Sulfur must have to be assigned an oxidation state of +6 to add up to 0. Let's look at a nitrate ion. Now here is something a little bit different because we're looking at a polyatomic ion. The sum of the oxidation states must add up to the charge on that ion, so it must add up to -1. We know oxygen is -2. -2 times 3 gives us a -6. -6 plus 5 would give us an overall charge of -1. So the oxidation state on nitrogen would be assigned as +5. If we look at potassium chromate, well, potassium is a monatomic ion, so the charge on the ion is the oxidation state. Oxygen is -2, and since this is a compound, it has to add up to 0. So -2 times 4, that gives us a -8, plus 1 times 2, that gives us a +2. So we're looking at a -6 overall. Chromium in this compound must be assigned a +6. That would give us +2 and +6 +8, and -8, which would add up to 0. So last one we'll look at is a carbonate ion. So -2 for oxygen times 3 gives us a -6. It has to add up to -2, so carbon must be a +4. A +4 and a -6 adds up to -2. So let's determine the oxidation numbers for each of the atoms in the following reactions. Okay, so we're going to look at sulfuric acid and sodium hydroxide to produce sodium sulfate and water. All right, so we know that oxygen is going to be -2. So let's just do that across the board. -2, -2, -2, -2. We know hydrogen is going to be +1. So +1, +1, +1. We know that sodium is going to be a +1 because it's a monatomic ion. We have to figure out what sulfur is. So this has to add up to 0. -2 times 4 gives us -8. +1 times 2 gives us +2. So sulfur is going to have to be a +6 to add up to 0. If we look at sodium hydroxide, +1 -2 +1 adds up to 0. So we're good here. +1 times 2, that's a +2. -2 times 4, that's a -8. So sulfur must be assigned a +6. +1 times 2, that's a +2. -2 times 1, that's a -2, so that's 0. So we've assigned all of our oxidation numbers. Now we want to look at the oxidation numbers on both sides of the reaction. Hydrogen on the reactant side and on the product side is +1. Sulfur is +6, +6. Oxygen on the reactant side and on the product side is -2. So we don't have any changes in oxidation state as we go from the reactant side to the product side. Let's look at another example. Copper is a free element, so it's 0. Silver is a free element, so it's 0. Silver is a monatomic ion in this compound, so its charge is its oxidation state. Copper is a monatomic ion in this compound, so its charge is its oxidation state. We know oxygen is -2, and we have to figure out nitrogen. Well, this has to add up to 0, +1, and -6, so nitrogen must have to be a +5. And here we can just look at nitrate. Nitrate has to be -1. If this is a -6, nitrogen must have to be a +5. Now we're going to look at the oxidation numbers on both sides of our reaction. Copper is a 0 here, but it's a +2 here. It's changing. Silver is a +1 here, and it's a 0 here. It's changing. Nitrogen is a +5, and oxygen is a -2. But here in this second example, we have changes in oxidation state. So our second reaction is an example of what we call an oxidation reduction reaction, or for short, we call it a redox reaction. any reaction in which the oxidation numbers or the oxidation states change from the reactant to the product side means that we had electrons that are transferred from one species to another, and we're looking at a redox reaction. So reduction in an oxidation reduction reaction means a gaining of electrons by an atom or ions. And think about that. If a species gains electrons, its oxidation state is going to go down, and that's what reduction means, going down. Oxidation is the loss of electrons by an atom. And you have to have both in a redox reaction. You have to have a species that's losing electrons and another species that's gaining electrons. You can't have one without the other. Now, a way to remember this, kind of a trick, is Leo goes Gur. Lose electrons is oxidation. Gain electrons is reduction. There are other ways to remember redox reactions, but Leo goes Gur is a pretty common one. Lose electrons, oxidation. Gain electrons, reduction. Now, two other terms that we need to know are oxidizing agent and reducing agent. The oxidizing agent is a substance that tends to gain electrons, or in other words, it's the substance that's being reduced. And if we think about that, in order for a substance to be reduced, it has to cause something else to be oxidized, and that's why it's called the oxidizing agent. The reducing agent is a substance that tends to lose electrons. And again, that makes sense because in order for it to lose electrons, it has to cause something else to gain electrons or to be reduced. So your oxidizing agent is the substance that's reduced, and your reducing agent is the substance that's oxidized. So here's a little graphic to kind of sum this up. If we have a metal M and a nonmetal X, the metal is going to lose electrons and become a positive ion. That electron is going to go to the nonmetal, which is going to gain electrons. So the substance that's oxidized is losing electrons, its oxidation state is going to increase, and it's the reducing agent because it's going to cause the other substance to be reduced. The substance that's reduced is going to gain electrons, its oxidation state is going to go down, and it's the oxidizing agent because it's going to cause the other species to be oxidized.